This is the brief on modeling concentrated charge distributions using delta functions. So, we're going to look at how physicists use this really neat tool, the delta function. You can think of it kind of like a mathematical switch, and they use it to model charge that's been squashed onto, say, a thin line or a flat surface. And we're going to see how that totally changes the electric field you get, especially when you compare it to a good old-fashioned point charge. Okay, let's dive into the three big ideas here. First up, and this is the kind of tricky part, it's all about the dimensions. See, to model a one-dimensional line of charge, you'd think you'd use a 1D function, right? Nope. You actually use a two-dimensional delta function. The reason is that function has to pin down the other two dimensions to make sure the charge can only exist along that single line. And then, it's the other way around for a flat 2D surface. For that, you only need a simple one-dimensional function to lock down that one axis that's sticking out. Okay, second. This whole dimension thing, it directly affects how intense the field is. It's pretty simple, really. The lower the dimension of your charge, so the thinner the thing you're modeling, the smoother and less spiky the electric potential gets. And finally, let's just compare them all. A normal 3D point charge gives you that super sharp field, the one that drops off really fast, like 1/r. But if you spread that same charge out onto a line, well, you get a much gentler logarithmic field. And here's the kicker. When you spread it across a flat 2D surface, that sharp point, the singularity, it just vanishes. Instead, you get this really smooth, linear potential right near the sheet. So the bottom line is that while the delta function is an awesome, flexible tool for modeling all these shapes, that classic, super sharp field behavior, that's really the unique signature of a true point source, and only a point source, in 3 dimensions.